Hello, this is part 2 on our section for regression for nonlinear data. And just to remind ourselves, we're working with power functions for this part, and we're trying to transform this into a linear function because regular regression didn't work. And so if we take the logarithm on both sides, we end up with something of this form, which if we consider the logarithm of the data to be our new x and our new y, then we basically have a linear relationship. And notice if I call this, say, A, then what I really have is the natural log of little a equals capital A. And so A is equal to E to the capital A. And that'll be important here in a minute because when I'm trying to solve for my intercept, I want the original intercept, not the logarithm of the intercept. And so if I am in fact using this transformed data, I have to transform back, and this will be the way back. Notice the b value, which is the slope, was unchanged. So there's no transformation in either direction there. Now, this will only apply in certain situations, but once we get into it, you'll see what I mean. So let's take a look at some data. So here is some data about our 8 planets in our solar system. The first column is the distance from the sun in millions of kilometers, and the second column here is how long the year is. So you can see Earth is 365 days. And the question is, what's the relationship between these two columns? And if we want a visual of what the data looks like, there's the picture, and we can see there's definitely a relationship, but it's not linear. So a power function is certainly a reasonable enough assumption, especially since presumably the closer you are to the sun, the closer your period is to 0, and so a power function is a decent idea for a first try. So let's see the transformation in action. So what we're going to do here is the log of x and the log of y. And so I'm just going to let Excel do those calculations for me. And so I'm just dragging that down to let Excel take all those logarithms. And so the point here is that if I plot the transformed y versus the transformed x, I get a very nice linear function. So this would be an indication that a power function was the right choice. Now I can apply normal linear regression, which we have that here on Excel. So I want a linear fit. Let's go and look at the equation and the r squared value. Notice Excel saying an r squared of 1, so that means it's about as perfect as we could hope for. And now we have our slope, which is about 1.5, and our intercept, which, remember, this is the log of the intercept, so negative 1.6184. So if I want the original a, then I need to take the exponential, so exp of negative 1.6184. And we get 0.1982. So our model then, we could try it out to see how good it does. Our model then would be 0.1982 times this raised to about the 1.5, 015 power. And so we get a pretty nice fit. Notice pretty much on the mark for the first 4 planets. Get a little bit of error, but in terms of percentage error, that's still pretty good. What is that? 200 days out of 60,000. So that's still a nice percentage error. So that is the way of doing it with a spreadsheet. And the long way, we can also use the shortcut that Excel provides since it can do these calculations directly. So if we wanted to let Excel do the trend line for us, notice we can go to add trend line. We can hit power, ask for the equation and the r squared value, and sure enough, we get 0.1982 times x to the 1.5 with an r squared of 1. So, in general, it makes sense just to do it this way. That other way illustrates what's going on behind the scenes, so we understand why it does what it does. And as we said, since this is such a great fit, we don't have to worry about our cautionary warning about the transformed SSE not being the same as the original SSE, because they're both really close to 0. And that's because this is based on one of Kepler's laws. And so we're not surprised that we get a nice fit, because the law says that, yes, this power should be 1.5. And so there's a little bit of a round off error there in our calculations, but the actual error or power is 1.5. And of course, these distances are averages over the whole orbit. Now, before we wrap up with this example, I want to try one other thing, and that's to analyze this in a less advanced way, actually use something called log-log paper. So let's go to some log-log paper and see what that looks like. Okay, so here is log-log paper, and I encourage you to check out chapter 3, where we talk about both using a spreadsheet and using graph paper to help us with these models. So if you're comfortable with the basics, then we'll jump into our example here. So what is our data? The first data point is Mercury, which is about 58 million kilometers away, and 88 days for its period. So I want to plot 58, 88. And the nice thing about log-log paper is this is doing the transformation for us. So when we were looking on Excel and we had to find the logarithms and then plot the logarithms, all those calculations that the spreadsheet had to do, the paper does for us. And so what we can do then is we need to set our scale to match the data that we have. So as a reminder, our data runs from 58 million to 4,500 million, or we're not going to use the millions, so just 58 to 4,000. So notice that's 3 orders of magnitude, which is good because we have 3 cycles on our log-log paper. And so what that means then is I want to count this as 10, 100, 1,000, and 10,000. Likewise, our period of our planet runs from 88 to 60,000. So we want to reflect that on our vertical axis. So this will also be 10, 100, 1,000, 10,000, and 100,000. So now we know we can fit all of our data into the graph paper that we have. So recall we said Mercury was 58, 88. So 58, since we're going from 10 to 100, that means this would be 50. So 58 would be about here somewhere. 10 to 100, that means this is about 80. So 88 would be about there. So if I follow that along, I'm getting somewhere around there for our first data point corresponding to Mercury. So I encourage you, go ahead and practice your log-log plotting. Here's the rest of the data, and then you can compare to what I get here, as I will go ahead and plot them right now. One has to be careful on this one. Notice we're having 100 to 200, and there is 4 lines here, so this is about 125. Venus is 108, so 108 would be in here somewhere, and then 225 would be somewhere around there. Likewise, Earth 150 would be on this next line, and then 365, there's 350, so maybe there. Mars is 227. I've got I've got 200 to 300, so 227's about here. And we're going up to 687. So 687 is going to be about here. Notice it's looking linear, so looks promising. We'll do one more here, just because we don't need all the data points since it's such a good fit. But 778 for Jupiter and 4329. 778 would be about here, and 4329 would be about here. So come up to here. So maybe there. And maybe we can go ahead and do Neptune since it's the largest one. So 4489 would be about here, and 60,000 would be up here. And so once again, somewhere around there. All right. So there's a few planets left there you can try on your own. But overall, the good news is it does appear to be linear. We can try to fit a line through all these points. We get a great fit, so that's encouraging to see. And so now we need to find the slope and the y-intercept of this line. And by intercept, notice we're going to mean where it intercepts 1. So that's going to be a problem on this one because 1 is actually going to be down here off the page because this is at 10. So crossing this line is not the one intercept. So that's not the one we need. I would have to go this far over and then come down here. I'm not going to try to do that. We'll do a different way here in a minute. So let's do the slope first. The slope is actually easiest to find, not using rise over run, but to think about something similar, and that's the tangent, right? If you think about, if I did a normal rise over run, we might have something like this for the rise, and then say something this for the run, and I think about that angle. Then notice rise over run, the tangent of that angle is equal to rise over run, which is my slope. So that's what I really want, is the tangent of this angle. So I will just pick a spot here, doesn't matter where on the line. And notice, looks like around 56 degrees. All right, so tangent of 56. So B is the tangent of 56 degrees. And then to find the intercept, I'll just plug in to find A. Because we know that y equals A times x to the B. And since I know B is tangent of 56 degrees, and I know x and y are, I can use any one of these dots, then I should be able to get an answer. But let's figure out tangent of 56 degrees first. So the tangent of 56 degrees is, and sure enough, we get about 1.48. So again, the accuracy of something like this isn't going to be perfect, but at least to one decimal place, we get B is approximately 1.5, which is what we wanted for Kepler's law anyway. So I know B is about 1.5. I want to find A, and I know that y equals A times x to the B. So let me use Earth. I know the y value for Earth is 365 days. A is what I'm solving for. And Earth, the distance is about 149.6. And then I raise that to the 1.5 power. So I need to solve that for A. So we'll just use our calculator here to do that calculation for us. So 365 divided by 149.6 to the 1.5. And the good news is that we get about 0.2. 0.199, which is very similar to what we had before. So overall, our model, if we wanted to summarize, is about 0.2 times x to the 1.5 power. And probably no point in being any more precise than that when we're using the log paper. We could certainly use other technology to refine that if we needed to. But the good news is this was such a great fit, such a great model, that the spreadsheet solution was good enough. That won't always be the case, but in this instance it was. So that's it for this example. We'll look at another type of function in the next video.